I'm setting up the stream too, okay. So it'll be streamed, okay? All right. Yeah, you can get rid of that. You can get rid of it. Get rid of it. Get rid of it. Yeah. What is your presentation? Oh, I see. I got it. All right. All right. All right.
So, not to recycle, but to like stop manufacturing.
Oh, they made a new one for this?
Yeah. That's why I thought, it's a little bit.
Oh, they made a new one for this?
Yeah. That's why I thought, it's a little bit.
Oh, they made a new one.
Yeah.
Like, I don't know. You guys enjoy me playing it? Do you guys?
Yeah, I thought so too, but it was an idea.
All right. Okay. Before we get going, my friends, hey, make sure that if you will be so kind, give us a follow. MDC Robotics in YouTube and MDC Robo on Twitch.tv. We're going to be live streaming our little things there. All right. Thank you so much. All right. Let us start. Okay. So the floor is yours, my friend. Actually, so the camera can see it, actually, but better if you put it over there. So this is the camera, make sure. Kind of like, there's good. There's good. You got it. We'll get a better camera setup.
Okay. Hi guys, my name is Mauricio. I'm part of the Robotics Club. I'm going to talk to you about a project that I did a couple of months and still working on it, but it's almost to the point of completion. It is related with the automation of a photolithographic process. That means that, can you go ahead? This is an example of it. Basically, with light, we're capable of this technology, and there's a gel that solidifies with the exposure of light. And you can see that this gel, it's liquid, but once it is in contact with this light, it turns into a solid and you can create certain shapes with it. That's why we're doing. These shapes have many applications in our engineering. And the project is related with creating these shapes. It's not really application, but automating this process, because this process was previously done by the professor manually. This is the hardware that we're using. We're using a motorized microscope stage. Basically, the way I can program the creation of the shape. We're using the beam of light. This beam of light is what is solidifying the gel. It's another term. It's called photogravure. And this is the device that was where I'm creating the shapes. Those shapes that we saw previously, they're created inside of here. It's called a microfluidic device because these shapes are microscopic. Okay, go ahead. Next slide. And this is the software this is an explanation, a very simple explanation of what I did. Basically, I created an interface. This is a representation of the interface in which the professor draws a pattern, a shape. In this case, these are called L shapes. He draws these shapes, and the microscope stage moves. Can you play the video so you can see? The microscope is maximum because it was previously what I was trying to explore. So that's more or less the thing. As I first, the professor creates the shape by drawing it in the computer, and then someone does it. Okay, before I get into this, the main issue and why the purpose of the project is that to create this more precisely and in a more time efficient manner, because the beam of light doesn't solidify that gel that quickly. It takes like 30 minutes, and the shapes are microscopic. So the professor had to do that manually, and it took him weeks to do something that now we are capable of doing in 30 minutes. These are some tasks that I had to do to attack this project. For you to know, I started this project without any experience in programming. I started this project like 4 or 5 months ago, and as I started, I dedicated like the first 2 weeks to starting to learn programming. And these are some of the major aspects that I completed. For example, I had to, how can I communicate with the microscope? It was through serial communication. Serial communication is through cables, and it's something similar to USB. USB is a similar type of serial communication. Then I had to find a way to, as I clicked out that cell that I created, that grid, convert that into coordinates so that the microscope could, so that I could send those instructions to the microscope. I also need to document what was the scale, the size of the beam of light, because as I use a different lens, for example, if I use a bigger magnification, the beam of light gets smaller. And that I needed to document that, like how small I needed to measure it. Also the acceleration of velocity, because it's something that has to be very precise, and I need to control the movement very well. And finally, this has to do with the serial communication. Baud rate is the amount of has to do with the information. How fast can I send the microscope the information? Okay, next slide. This is some videos of the prototype. This one first, Felipe.
I've been working on improving the program.
Okay, this videos of July. I started the program on Python. These are productions. You're going to see here that when I run the program, there's
more
as I
complex
click
structures in an easier
the interface, that is sending 3.5. That is storing more close coordinates. And then you're going to see here
needs
on
to
the back.
go to.
Very quickly, this one.
And then they will be
This is the file that has the coordinates. And they go into the microscope.
by another,
And then
they are
the microscope
instructions.
reads
So
those coordinates and so
here
that's
the
the
coordinates
basic
with this,
concept.
they close the window, they are going to run it, they are going to create another file.
This language is Python. And then after I did that, you can see that it is moving. Okay? Next slide. Very good. Okay, and this is regarding the dimension. I took some images of the beam of light.
Sorry.
I projected the beam of light in 3 dimensions. This is the intensity, so I needed to know how big was it. That's part of the scaling aspect, as I told you. And then I used that information. I took a picture of a ruler, and it's like a unit conversion. How many pixels translate to? This is like 1, 4, 5, like 3.6 millimeters. So I use this number in 0.6 millimeters, this amount of pixels, and then I translate that into a unit of length. Okay, next slide. And this is a closer image of the interface. It has the window of the interface on top of the file. As I click, for example, 2.0, that would be this one. It is converting those coordinates into structures for the microscope. Very good. These are close image of the documentation. As I said, if you see the view of light from the top, it looks like this. Then I projected it into 3 dimensions to see the intensity, and I cut then to obtain this distance. In that way, I could measure how wide was it. This is full width at half maximum. So then this amount of pixels, I translated that into the unit conversion as I told you previously with the ruler. And in that way, for example, this 10 times objective length has a width of approximately 200 microns, which is 0.2 millimeters. And now there's another problem that I had. It was regarding the alignment process. Because one thing is, in the perfect world, this is my interface, for example. As you see, all is 90 degrees, and it's perfect. If this is the same as this, so if I click on this, I give the microscope these instructions that go right, go down, then it will translate perfectly to this if it was perfectly aligned. But what really happens is that you saw previously that the container is put in the microscope stage. Because it's microscopic, it isn't aligned perfectly. So there's an alignment issue that I need to solve, and I realized that at the middle of the project. How I solved it? Any ideas how I solved it? By seeing this? Yeah.
You can take the angle between the real and the virtual, and then you can find the angle by sine.
I use sine and cosine. There's a function in trigonometry that I have to look up. Basically, I find this angle. I first go to a corner of the container. The pink thing represents the container. So I go to a corner of the container. I select a corner. Then I move. You're going to see, after this slide, you're going to see better. I obtain another point, and I calculate the difference that in between this. That I get the slope, and that gives me an angle. And then I use that angle to rotate every point. So every point that I click here, I rotate it. I rotate every point so that it aligns with the real world. Okay, next slide. This is an illustration. For example, this is the ruler. You guys can see that this is precisely here, right there in the bottom. But as I move here, I basically move the ruler like this. First here, the second point here, and it was actually a little bit off. That inclination, I then move the microscope stage like this. I select that point again, and the difference between those points gives me a slope. Like have 2 points, that gives me a slope, and then I obtain the angle, and that lets me rotate every point. So I rotate my drawing, the interface, it gets rotated, and by this angle. Okay. Now this is a testing I did. As I mentioned previously, this is a gel that gets solidified with the light. You guys can see that I use, for example, the 10 times magnified objective length. This has a length here of 2 millimeters, and the width is 0.2 millimeters, which is 200 microns. And next one. We were testing how well it solidified. And you guys can see that this was August 15. Then after 2 days, it looks like blurry because apparently what happened was that it solidifies from the bottom. Lighting is on the bottom. So it is like not getting solidified on the top. So after 2 days, we were able to see, by flowing liquid, that this part on the top wasn't solidified, as well as it's seen here. And these shapes allow us to understand what is the correct setting that we should use, the correct velocity, the correct dosage of light with the speed and also with the intensity. That's the purpose of these testings. Okay, next one. Now you're going to see a bigger issue that I found. A bigger issue, look how messy this looks, right? It doesn't look properly. This is smaller than the previous one. Go back, one slide, go back.
Hold up.
This is just trial and error. I was learning as I did the project. You guys can see that the effect is not noticeable. But what is happening is that at the beginning there's a center here, the center of the path. And at the beginning there was an algorithm that made the microscope stage move like a certain distance and go back, go forward. I realized that once I make the lines thinner. Now this is 20 microns. For you to know, I think that one hair is the same, is like 5 times bigger. One hair is like 100 microns. So this is thinner than a hair. And this has a length of 0.5 millimeters. That's 500 microns. I then could realize that there was an algorithm that was causing this ugliness. I fixed it. It was just a setting. I had to put that setting to 0. Like this, it is called backlash. I set the backlash to 0, and now in the future we're going to obtain straight corners, not like this, that they look so messy. Okay, thanks. And now what happens is that scientists and engineers, they use better tools. For example, a better tool is MATLAB. MATLAB is the tool that the professor wants me to because this is a tool that's going to be given to him for him to utilize, so it's better that he's able to modify and understand it better and that way. Because he's more used to MATLAB, it was like he asked me to do MATLAB because he's more used to it, and it's a tool that after this project ends, I'm going to give to him, and he has to be able to understand the tool perfectly. And now I'm doing MATLAB. This is what I was learning. Now the interface looks a lot better. Please simplify. There are some settings that you're not seeing because of simplicity for me to explain. But this is the main concept, like you're clicking the buttons and they translate into coordinates. And this was a previous illustration of the interface. Skip it.
And that's it.
That's it. Well, let me go back. I think I can explain this well. This interface was that the main concept is that the main idea is that every cell, small cell of this grid, represents how big is the unit flag, because that is what is going to determine the thickness of the lines, basically. So that was the concept, that this is a point where the unit flag is going to position itself, and then as I select those, it is going to move the microscope stage, and that is the unit that represents every cell, the unit flag. How big is it? Okay, any questions?
Bravissimo! Hey, good job. Oh, thank you so much. Hey, come here. That was good. All right, that's amazing. Yeah.
This has been a very good learning experience because I started with Python because you can find online which is the simplest programming language. You're going to find that it's Python to learn at the beginning. But then the professor told me, hey, I need it on MATLAB because that is a language that I'm used to, and it's a tool that I need, and it's obvious I want to leave this as a good project. And then I had to then learn MATLAB. What it was, I had the problem solved, I just needed to translate them.
It's easy, right? If you already have some programming experience, then like translating becomes easier and easier, right?
Yeah. And MATLAB in this case was simpler because MATLAB differs in, it has that difference to Python because Python has a lot of libraries. It is just, Python is basically sending instructions to a computer. While MATLAB, you have also certain stuff that is built into the program, such as buttons. It is more friendly to work as an engineer. So that's why the professor required me to please do the MATLAB, so I did MATLAB. And as you guys can see, I had a lot of errors and that ugly shape that I did, or that helped me learn. So this is a learning experience now. So I think that the conclusion, if you guys are interested, it would be very nice that you to learn. I think that the best method is to get into a project, a very simple one, and then start progressing and learning. That's going to help you a lot.
To learn what? What was it? To learn MATLAB?
No, to learn any program. Like, instead of, in addition to reading like a for loop or
Going to a class, like
going to a class,
right?
taking a class, doing a project, a very simple one, like let's do an interface that a calculator. That helps you a lot. That's I think that I'm a better programmer thanks to this learning experience, this program.
Awesome.
Take the chance, guys. That's very important. This guy, he was like, I don't know if I can do that.
Yeah.
Just go for it, man. Like,
At the beginning, I called Felipe. I had to consult with because there was a time limit, a time frame to do the project. And I called Felipe. Felipe, with my 0 level of experience, do you think that I could progress? Do you think that I could do certain progress on the project? The expectation to the professor, whether for me to finish the program or to be able to create those shapes as you guys saw in the testing. And thankfully, learning and asking a lot of questions to Jonathan, to Ruben, to people in YouTube that answer my comments, I was able to do the program and it's working. So it has areas of improvement, but it's working.
as I tell you guys too, like you don't need to know this stuff, but what I want you to come here is want to learn. That's all you need. Like you gotta come here, you keep coming, and you'll get there. That's what it is. They've improved this guy. Good stuff. So yeah, it is. It's great. I am very proud. Good stuff. And yeah, like you gotta take the chance. Go for it. You were scared when you first started, right? It was like crazy stuff, but you learn.
It sounded like the biggest mountain that I need to face.
It's good stuff. So thank you so much, man. Yeah, it's good stuff. We're gonna keep going. You guys can keep going with your robots and stuff. I'm gonna close the stream. We'll have a meeting discussion about the stream, but it went well. Thank you, everyone. Thank you. Good stuff.